Hi, Saxon Math Course 2. This is week 1, and we're going to be working through lessons 1 through 4. So these lessons are also the lessons in your text. You can follow along with your text. Just use the screen. Just hear the way we're discussing it. Feel free to read your text if you'd like, and we're just going to work to support you in many ways so we can look at it visually together. All right, let's look at example 1. So we're talking about arithmetic with whole numbers and money, and we're going to be dealing with variables and evaluation. So we've got some good math going on here. The first example is about adding, and I'm pretty confident you all know what you're doing here, but I just wanted to remind you how important it is for you to line up each of the numbers when you're adding them such that the numbers in the ones place are lined up with the numbers in the ones place. Numbers in the tens place are lined up with the numbers in the tens place, and we continue that with the hundreds place and the thousands place all the way as far as we go, as far as it goes. And when we're dealing with money, I want you to check this out. We've got $1.45 here. We have $6 here, and then we have 8 cents. Recognizing exactly what type of number we're dealing with is really instrumental in figuring out how to line them up correctly and have a successful math problem. So this is the way I did it, lined it up, added them together, made sure and carried my information where I needed to. So that's example 1. If you have questions with it, when we get a chance to see each other, let me know and I'll happily show you how to do this addition. Subtraction is very similar. This looks a little bit more confusing because I did my borrowing, but it's so necessary to line everything up. Indeed, lining up the ones place and the tens place and the hundreds place is going to be what you need to succeed. And so you'll see here, 7 cannot abide by removing 8 from it. You can't take 8 from 7, so we had to borrow, couldn't borrow from the 0, had to go over to the 2 lent 0, 1, became a 10, 10 became a 9, and then we got 17 here. Whew. So 17 minus 8, 9 minus 4. Now this 1 that was here had to borrow from this 5 to make it an 11. And so this 5 became a 4, and 11 minus 9 is 2, and 4 gets dropped down here. With this problem, I almost wanted to just say, well, I know $5 minus a quarter is $4.75. I kind of recognize that. But it is important here to also keep in mind lining things up if you're going to do your subtraction in a long way. So you could think about this as making sure you're writing everything in the same way. $5, and this is $0.25, if you can think about it that way. So we line it up, and we do our subtraction, we borrow as needed, and we keep it moving and grooving. Again, if you have any questions with this problem or the one before, adding or subtracting, let me know. Multiplying is where we start to get into some concepts that we may not have seen before. So here, I want you to observe that this is multiplication and this is multiplication. And when no sign is given and you've got parentheses around a number and then a number not in the parentheses, that's multiplication as well. So if I were to rewrite each of these, what I'd write for the first one, part A, would be simply 164 times 23. With this next one, part B, a couple ways to do it, but I'm going to go kind of old school straight out, and I'm going to write 4.68 times 20. For part C, we're going to have, and this might not be the way you do it, I'm going to write 0.29, sorry about that, changing the problem there, 0.29, which represents my 29 cents, times 5. And then I'm going to proceed with multiplication the way I usually do. And so I know everybody has their own method, but I'm going to go old school. 3 times 4 is 12, carry my 1. 3 times 6 is 18, plus 1 is 19, carry that 1. 3 times 1 is 3, plus 1 more is 4. This 2 is what I'm multiplying next, but that 2 is not a 2. It's really a 20. And so since I'm multiplying 20 times 4, it means that everything will have a 0. This whole set of things that I'm going to multiply will have a 0 in the ones place, and it's kind of shifted over. So 20 times 4 we know to be 80, right? And then we'll keep going. 2 times 6 is 12, carry my 1 here, and then 2 times 1 is 2, plus 1 more is 3. Adding all of that together, I end up with the following. 3,772. Here, I'm going to multiply this 20 and this 0. Sometimes we just multiply by the 2, add the 0 at the end, but I'm going to go old school as I mentioned. I'm going to multiply everything by 0, and 0 times 8, 0 times 6, 0 times 4, all 0. This 2 is really a 20, so I'm going to put this 0 here as a placeholder and multiply through. 2 times 8 is 16, 6 down there, carry my 1. 2 times 6 is 12, plus 1 more is 13. And then 2 times 4 rather is 8, plus 1 is 9. Adding all of that together, I get this value here, 9,360. But wait, I didn't account for the decimal place. So I've got 2 decimal places in one of the factors that I'm multiplying. So then I'm going to repeat that here in my answer, and I see that the answer to that is $93.60 if I were multiplying $4.68 by 20. Finally, down here, I'm going to multiply 5 times 29, or 0.29, and I'm going to get 5 times 9 is 45. 5 times 2 is 10, plus 4 more is 14. And I'm going to move my decimal place over 2 times, and when I do that, I get $1.45. I'm hoping that made sense, and I'm not always going to be explaining the multiplication because I think you should have learned how to do that at another time. But if it's giving you trouble, please let me know so we can work on it together. Here we're going to do some division. Both of these are ways of looking at division. So division can be the simple division sign that you remember, line with 2 dots over it, but also division is this fraction symbol. So let's go ahead and rewrite these problems. So here's the rewrite of each of these problems. Notice that we have the dividend, the number that's being divided, then the divisor, the number that's doing the dividing, set up in the way that we would if we were doing long division, which we're about to do. So let's see, 56 cannot go into 1, 56 cannot go into 12, and 56 can go into 123. And so that's where I'm going to put my answer. That's where I'm going to start. So since 56 can go into 123 about 2 times, I'm going to put a 2 here. I'm going to multiply 2 times 56, and when I do that, I get 112. I'm going to subtract that, and I get from 123 subtracting 112, I get 11. I'm going to drop this 4 down here. 56 goes into 114, well, another 2 times, because I know 112 is what I get when I multiply 2 times 56. So I'm going to write that back down here again, subtract, get the 2, and there's a couple ways I can write this. I can keep going, but I'm going to stop for now and just write that my answer has a remainder of 2. The next thing we're going to do is divide 5 into 12.60 or $12.60. 5 can't go into 1, but 5 can go into 12, so we're going to start our work there, making sure that we put our first digit over this 2. 5 goes into 12 2 times. 2 times 5 is 10. When we subtract, we get 2, and then we're going to bring down the 6. I'm not going to bring down the decimal point, but the decimal point needs to be up here on the quotient line. So now 5 goes into 26 5 times, because I know 5 times 5 is 25, and that means that there's just one more left. I'm going to bring down this 0. 5 goes into 10 2 times. 2 times 5 is 10, and I'm done. So my answer is $2.52. That's the quotient. All right, so the cool thing here, before we get to the problem set, is this. This is giving us a little bit of a taste of algebra. So remember, algebra uses like lots of letters in the math problems, and so what you want to do is be able to observe that sometimes the letters always represent a number. And so in this case, X represents 10 and Y represents 5. So when we evaluate, we're going to plug in the numbers that are represented by the letters. And this is good practice for us to start thinking algebraically. So if X is 10 and Y is 5, we're going to have 10 plus 5 when we're adding X plus Y. And we can do that pretty straightforward. We know that that answers 15. In part B, we have X minus Y, which we can rewrite as 10 minus 5. And we know that answer too, that's 5. C is going to be XY, which really means when there's no symbol given between, it means to multiply. So this means 10 times 5. We know that is 50. Our final example is part D here. We have X over Y, or X divided by Y. And so what I do is say 10 divided by 5. And the answer to that is 2. I hope this made sense. I hope this is good for you and you understand it. This practice set, I expect you to do all of it, and you'll do the portion of the other practice that comes after that I mentioned to you before. So be sure that you get all of these problems done before you say you've really understood this section. Also, if you want to check your answers, you can go to Quizlet and you can type in the textbook name, which is Saxon Math Course 2. It's coming up. And what you'll see is your textbook. Scroll down a bit. You'll see your textbook and you can click on it. Once you click on your textbook, they'll give you access to all of the answers for each chapter. And so you'd be able to click on the chapter, look deeply at the answer choices that are given, and they'll give you the answer to the practice set and answer to the written practice. So if you're having trouble, please make sure you check your answers so we can know which ones are right. You are responsible for checking your answers, all right? Now here we are with lesson 2. Lesson 2 is going to talk about properties of operations. And so we have these properties. I'm going to go over them because I think they are just vital for understanding some aspects of math, and you just want to feel confident with it. So the first one is the commutative property. Now the word commute makes me think of the drive to work, moving from one place to another. When you commute, you move from one place to another, and that's what the commutative property is showing us here. If I have A plus B, it's going to be the same thing as if I move them around and had B plus A. So this is representing the commutative property over addition, and we can also do the commutative property over multiplication because the order in which I multiply does not change the value of my product, and the order in which I add doesn't change the value of my sum. So the commutative property, think about moving or going to work, moving things around, right? To commute means to move. When we move it around with addition and subtraction, it still is equal. All right, we still have an equal value. All right, so let's look at this next one. This next property is the associative property. And I think about who I associate with, right? Who are my friends? And so in this case, if I have A plus B plus C, and I choose to organize myself in a particular way first. So if I have A and B, I add those together, then I add C, right? Or if I have A and then I add B and C later, we get the same answer. And I think about associating, like if these two guys are friends and then they add this guy into the friend group, or if these two guys were friends first and they add this guy into the friend group, it still amounts to the same group of 3, the same value. And we can look at that in terms of multiplication as well. The order in which we multiply the same 3 numbers will yield the same exact answer. So if I had to multiply 3 numbers together and I chose to multiply A and B first, then C, I'm going to get the same thing as if I multiply B and C first and then A. So that is the associative property. Think about the way things are associated there. So the next property is the identity property. Who do you see when you look in the mirror? You see yourself. And so that's kind of like looking in the mirror, you see your identity. So A plus 0 gives us A again. A plus 0 gives us A again. And A times 1 gives us A again. So this is the identity property. We're always going to get the same value. If I have 5 plus 0, I get 5. If I have 2 plus 0, I get 2. If I have 3 times 1, I get 3. If I have 7 times 1, it doesn't matter what A value is, but whenever I have a number and I add 0, I get that number again. Or if I have a number and I multiply 1, I get that number right back again. And this final property we're going to talk about is the property of 0 for multiplication. So basically, doesn't matter what number we multiply by 0, some number a. If I multiply it by 0, I'm going to get a. 5 times 0, I'm sorry, I said it wrong. Let me try it again. So what this property is showing, that it doesn't matter what we multiply by 0, we're always going to get 0 as the answer to that product. So if I had 5 times 0, I get 0. 2 times 0, still 0. Negative 375 billion times 0, I'm going to get 0. So a times 0 is always 0. Let's look at some of these examples. So one of the things they often will ask you to do is to see if you can identify what the property is that is being illustrated in a problem. And so we're going to do that by just observing. We've got 5 times 3 is equal to 3 times 5. Notice things are moved around, they commuted. This is the commutative property. Commutative property. And over here, we have 3 plus 4, and then we're adding the 5 in. But here we've got to add the 4 plus 5, then add 3 in. This is definitely the associative property. We're seeing how these numbers associate together. Associative. Okay. Here we have 6 plus 0 equals 6. We have the identity here. We have 6 kind of looking in the 0 mirror, and we get 6 back. So this is the identity property. And here, 6 times 0, doesn't matter what we're multiplying by 0, we get 0. This is the property of 0 for multiplication. I'm going to put prop of 0 for multiplication. All right, so we're going to be asked to do that. So that's going to help you get more familiar with these properties. All right, so which property can we use to find the unknown number? So we've got 8 plus something is equal to itself. The property, you know that's 0. The property that's being used here is the identity property. We know that when we're adding to get the same number on the other side of the equal sign, we're going to add 0. So this one would be the identity property for A. This next one is really the identity property for addition. This next one, part B, is asking a similar question. 1 times some number is equal to 9. You know that 1 times any number is equal to itself, so this is also a demonstration of the identity property. Identity property. Thank you for not laughing at my misspelling. Identity property, this time of multiplication. Over here we have C, which is 10 times some number is going to give us 0. Well, we know the only way to do that, the only way to get 0 in multiplication is for one of the factors to be 0. And so we know that this has to be 0 here. That's what that question mark would be. And we know that that is the property of 0 for multiplication. So property of 0 for multiplication. I'm getting all shorthand here. All right, let's look at this next. So looking at example 3 over here, we're going to use the new properties that we discussed to justify each step of this solution. Now, I'm going to be honest with you. I think that this is a neat exercise, but this is not something that I always want to force students to do. But I do think that it should make sense what we're talking about. So if you were given this expression, if you start off with this and someone says to simplify it and justify each step, basically you may want to do a few things. You may want to move some numbers around. So the first thing that they did here is they said, hey, I can move 25 over here and 15 over here. What gives us the right to move numbers around? Do you remember? It's that commutative property. So we see that the commutative property took place here on that first line. This next situation, if we're looking at what's happening here, we now chose to multiply the 4 and the 25 to do that first. And that makes a little bit of sense to me because when I see 4 and 25, I think about 4 quarters and I know that's 100 and that makes my life easier. But that doesn't tell me what or why we're allowed to do it. And we're allowed to do it because of the associative property. We can associate numbers over addition and over multiplication in any order we choose. So we can associate 4 and 25, do that first, and then multiply by 15, and we can feel confident that we have the same answer. And then so when we came from the associative property to this situation, not going to use properties per se. We're just going to describe what happened. So from 4 times 25 to 100, we just multiplied 4 and 25. That's how we got this particular step. And then here for this next step, it's not really a property that we're going to write down. We'll just describe what happened. We multiplied 100 times 15. And so that's the expectation. I always find it slightly unclear what they want us to do. I would rather you really understand what's happening mathematically than being able to point exactly exclusively to the correct property. But I do want you to know the properties. All right, with that in mind, you see the practice set is here. And after the practice set, you have your other set that goes over the problems. Do exactly the assignment that you were asked to do, always doing all of the practice set to make sure you understand everything to the best of your ability. Check your answers, and I look forward to talking to you about this soon. Let's go on to lesson 3. So here in lesson 3, we're going to talk about unknown numbers in addition, subtraction, multiplication, and division. So we're going to talk about how can we solve these things where we have unknown numbers. Also, we call them variables, numbers that are being replaced with letters in kind of a mysterious hideout kind of way. All right. So we have a couple of problems. Let's look at part A. It said find the unknown number. N plus 53 is equal to 75. Well, if I have this situation and I know some number plus 53 is equal to 75, I can look at this in a different way. If two numbers add together to give me 75, then I know if I take 75 and subtract one of those numbers, I should get the other. So when I do that, I get the value of 22, and I now know that n is equal to 22. So the strategy that I used is to undo or do the opposite of what the operation is telling me in order to solve for the variable. Part B is 26 plus a is equal to 61. If I add these two numbers together, I get 61. So if I subtract one of the numbers, 26, I should get the value of a. So let's go ahead and subtract those. We know we're going to have to borrow. And when we do that, we get a 5 here. And 5 minus 2 is 3. So we end up with 35. So what we know is that a is equal to 35. So this is how we would handle this situation. Let's take a look at this one. This looks so hard. In part C, we've got 3 plus 4 plus n plus 7 plus 8. All of that is equal to 40. So what we're going to do is use like our associative property of addition. We know that we can add things out of order if we want. So if I add 3 plus 4 and then add the rest of this stuff, it'll still be equivalent. So this is the same as 7 plus n plus 15. I can also add that 7 and 8 together. And if I can do that, I can move stuff around by our commutative property. And when I add that 7 and 15, I end up with 22 plus n is equal to 40. Now this looks a lot like the other problems we worked on. Since we know we can undo this addition by doing the opposite, taking that 40 and subtracting 22 in order to figure out what n is, let's do that. So 40 minus 22 is going to end up giving me 18. I'd borrow from this. This becomes a 3. This becomes a 10. I get 8. I have 18. So n is equal to 18. All of this work was for this bit over here, but I hope it made sense. Let's look at example 2. Here in example 2, the situation is flipped. Now we're doing subtraction. So let's think about what this means. If I have p minus 24 and that's equal to 17, that means some big number that I take 24 away from will leave 17. How can I figure out what that number is? Well, hopefully you recognize that the opposite of subtraction is addition. So if I were to add those two numbers, I would get that big number from which I'd subtract the 24 to get 17. So let's add them together. 7 and 4 is 11. And then I get 41. This tells me that P is equal to 41. And I'm going to just write it like that. This next problem, part B, is a little different. We have 32 minus some number is equal to 14. Now, just going to add these two together won't make sense because 32 plus 14 is going to be a bigger number than 32, and subtracting is going to be weird. I'd get negative numbers. What this is telling me is if I have 32 and I take away some number, I'm going to get 14. Then what I know is if I have 32 and I take away 14, I will get that number. So I'm going to do the subtraction here in order to calculate x. If I have 32 minus 14, I'm going to borrow from the 3, get a 12. I have an 8 here, this becomes a 2, and I get 18. In this circumstance, x is equal to 18. So here in example 3, we're going to be looking at multiplying. So remember, when there's no symbol given and we've got two numbers next to each other, a variable and a number, or sometimes we might have two numbers next to each other in like parentheses, like 2 and 4, we know that this means to multiply. So in this case, we're dealing with multiplication. We can look at this as 12 times n is equal to 168. That's part A. And we could look at part B as 7 times k is equal to 105. You can see the problem, right, with writing an x. Kind of looks like another variable. The x for multiplication doesn't really work as we move on to thinking about things algebraically and when we use like letters. So you might want to use the dot if you like, or you can just simply write 12n is equal to 168. Now, the question is, how do we figure out what n is? We figure out what n is by doing the opposite. If 12 times a number is equal to 168, then 168 divided by 12 has to equal that number. Think about it. So with that in mind, I'm going to write 12 divided into 168 will give me the quotient that is n. Whatever n is, we're going to get that here. 12 goes into 16 one time. 1 times 1 times 12 is 12. When we subtract that, we get 4. Bring down our 8, and we know that 12 goes into 48 4 times with no remainder. So that lets us know that n in this case is equal to 14. Over here, we're going to do a similar thing. We know we're dealing with 7k, and that's equal to 105. I know that if I divide 105 by 7, I'll figure out what that k is. So I'm going to do my long division like this. 7 can't go into 1, but it can go into 10 one time. When I multiply by 1 by 7, I get 7. I subtract, I get 3. Bringing down my 5, I get that 7 goes into 35 5 times. 5 times 7 is 35, and there's no remainder, and I'm done. This value is what k is equal to. K is equal to 15. The final example we have before our problem set is this. We're doing some division, right? Remember, when we have a fraction bar, we can think about it as division. So part A can be written as the variable a divided by 3 is equal to 15. Some big number that I divide by, I said the variable a divided by a. The variable a divided by 3 is equal to 15. Some big number divided by 3 is 15. That number, a, would have to be 3 times 15. Do you remember how to calculate 3 times 15? Hopefully you realize that it's 45, and we get that a is equal to 45. Let's do the very last example. So the last example, part B, is a little bit different. Notice the location of the variable. We have 64 divided by b is equal to 4. Now, this is very peculiar because it's not as simple. We have to figure out what we need to do. We are not going to do the opposite where we're going to multiply, but what we have to do is think about what's being said. This says 64 divided by some number b is equal to 4, meaning if I had some big number 64, divided it by b, I got this number 4. What I need to know is the number fact relationship, that 64 divided by 4 would have to be b. Think about it if you get confused. 10 divided by 2 is equal to 5, just like 10 divided by 5 is equal to 2. That's one of those number fact relationships that we have. We know that we can move around the dividend, the divisor and the quotient in order to create an equal relationship. So we're doing that here. We recognize that since 64 is being divided by b, that's equal to 4, that we could write this also as 64 divided by 4 is equal to b. Now when I divide 64 by 4, I can do long division if you'd like. I get 1 there in the tens place. This is going to subtract, give me 2. 4 goes into 24 6 times, and then I have no remainder. I'm done. So the answer here is that b is equal to 16. With that in mind, please feel free to get started with your practice work on your practice page in your text and do the other assignment that is associated. Check your work, and we will talk about this next section, lesson 4, in a moment. Here in lesson 4, we're going to talk about number line and sequences. So we know the number line, right? Number line, we've got numbers on it in order. We have the integers, that's the ones we think about, the whole numbers that are positive and whole numbers that are negative. So I'm looking at the number line 0, 1, 2, 3, 4, 5, and this continues on. But going in the opposite direction, we've got some negative numbers, okay? So these negative numbers can be looked at as losses, can be looked upon as losing, going downstairs, all different ways of considering negative numbers. So if you start on one floor and you go up the stairs, that's moving up positive. And if you start on that same floor and go down the stairs, you can think about that as negative, okay? So negative numbers can be put upon a number line along with positive numbers in this way. And this also helps us to determine which one is bigger and smaller. We know that the least ones are this way and the greater ones are this way. So things are increasing as we move from left to right. Arrange the numbers in order from least to greatest. Well, we can look at our number line and kind of help determine. We know that 0 is kind of small and 1 is bigger than 0, but -2 is, quote, smaller or lesser than them all. So here we've organized these numbers from least to greatest. In example 2, we want to rewrite the expression below by replacing in the circle with the correct comparison symbol. Let's remind ourselves of what our comparison symbols are. This symbol is greater than. It says whatever's on this side is greater than whatever's on this side. This symbol is less than. It says whatever is on the left is less than whatever's on the right. And of course, we know this symbol, this is equals to. So when looking at this example, we're going to put one of these symbols in this circle. And so if I have -5 and I have 3 on one side, I know that -5 is less than 3 because it falls further back on our number line than 3. So I'm going to put the symbol is less than like this, in which you may have remembered is back in the day we're supposed to eat the Pac-Man eats the greater one, or maybe the alligator eats the one that's bigger. And this is why, because this symbol, the way it's turned, it indicates different things. So is greater than or is less than, depending on the numbers on either side. Let's look. Show this addition problem on the number line. All right, so if we start off with a number line like this, we can actually think about addition and subtraction of numbers. So the problem says start with 3 and then go up 2 spaces. And if we did that 1, 2, we're ending at the number 5. So when we move up 2 spaces, that's plus 2 spaces, we end on 5. So we can see 3 plus 2 is equal to 5 by looking at the number line. We can do something similar by showing subtraction on the number line as well. So here we're going to start out on number 5, and the subtracting 3 means we're going to move in a backward direction 3 spaces, 1, 2, 3. And we see that we have arrived at 2. And so moving back 3 spaces, I'm going to write subtract 3. That's what's happening here, right? Lands us at 2. So 5 minus 3 is equal to 2. here, this is a little bit different. We're not used to subtracting a larger number from a smaller number. So in this circumstance, we will do exactly the same thing we did last time. We're going to start at the first number, 3, but minus 5 means we're going to go back 5 spaces. So we're going to go 1, 2, 3, 4, 5. Going back 5 spaces or subtracting 5 spaces, we end up at negative 2. So we can do these numbers, these subtraction problems where the subtrahend is bigger than the minuend, where the first number is smaller than the second number. That's what I'm saying. All right, so 3 minus 5 is actually going to give us a negative 2 as an answer. Let's look at this one. We have to simplify 376 minus 840. Well, this is kind of hard because I'm not sure what I understand here. I don't want to write a number line this long. Let's go back and see if we can see some inference from what we have done. So when we did 5 minus 3, the answer was 2. But when we switched it and we did 3 minus 5, the answer was negative 2. 5 minus 3, the answer is 2. 3 minus 5, the answer is negative 2. So it looks like when I subtract a bigger number from a smaller number, it's kind of like subtracting them regularly, but I get a negative number in the front. So let's try that strategy. So if I have 376 and I'm going to subtract 840, I should get the same answer as if I took 840, subtracted 376, and then made the answer negative. Let's go ahead and try it out. So 840 subtracting 376 is going to require me to do a little borrowing. And you guys are good at this now, so I know I don't have to explain to you all the things. But follow along. If you have any questions, definitely let me know. All right, so when I subtract the 2 with my borrowing, I get 464. But if I'm thinking about this in terms of the number line, I recognize that this 464 would have to be negative. Think about it. I'm here at 376. Zero's somewhere here. I'm going to go back 840 places. I'm going to end up somewhere with a negative number, and that negative number will be 464, negative 464. So my answer to this is negative 464. Let's look at this next example, example 7. The first 4 terms of a sequence are shown. Now sequences, guys, just patterns. So here's the first 4. We have 1, then 4, then 9, then 16. Find the next 3 terms. So in a way, we're dealing with looking for the next 3 terms. And so what we want to do is kind of think, what's happening? What is the pattern here? And I can see it because I play with numbers a lot and I think about numbers. But if you couldn't see what's happening, you might want to play around and say, okay, well, what's the distance between 1 and 4? And the distance between 1 and 4 is 3. And then you might say, well, what's the distance between 4 and 9? And that's 5. What's the distance between 9 and 16? That's 7. And so what you might observe is that these numbers are odd numbers increasing. They're consecutive odd numbers. So the next odd number jump might be 9, right? So if I add 9 to 16, I'm going to get 25. Maybe you didn't see that. Maybe you saw something else. Let's go ahead and try our odd number jump, and then we're going to look to see if we can see a different pattern. So our odd number jump would have us jump 11 spaces now because we're going up the next odd number. 25 plus 11 is 36. Next odd number is 13. And then 36 plus 13 is going to give us 49. So when I look at these numbers, I see this odd jumping pattern, but I also see something else. I know that number 1 is 1 times 1. I know that number 4 is 2 times 2. I know that number 9 is 3 times 3. And 16, you got it, it's 4 times 4. We can continue multiplying each of the natural numbers by itself in order to get each sequence value here in the sequence that we're looking at. What these numbers are called, you may have not heard this before, but they're called squared numbers. So I'm taking 1 and I'm squaring it. We have a nice way of writing this. 1 to the second power, it means 1 times 1. 2 to the second power, it means 2 times 2. 3 to the second power, you guessed it, 3 times 3. And so that's the pattern I saw, not necessarily the jumping ones. So there's often several ways to determine a sequence. There's no wrong way, but when you want to figure out the next three values in a sequence or the next three terms, you need to figure out what was happening to go from term to term in the beginning. Let's look at example 8. Here in example 8, we're going to, the rule of a certain sequence is k is equal to 2 times n. Find the first 4 terms of the sequence. Here's what we're going to do. We're going to recognize that n refers to the number in the sequence. So for instance, when n is equal to 1, that's the first number in the sequence. When n is equal to 2, that's the second number in the sequence. When n is equal to 3, third number, n is equal to 4, fourth number, you get it, n is equal to 5, fifth number. So what are these numbers in the sequence that are being defined as 2 times n? And so I'm going to fill in these boxes. They only ask us for the first 4 terms, but we're going to do all 5 of these. So if k, the number inside the box, is going to be 2 times n, 2 times the number of the sequence, the first number is going to be 2 because k equals 2 times 1 here. And that's going to give me that value. Here, k is equal to 2 times 2. K is equal to 2 times 2 is going to give me a 4. K is equal to 2 times 3 for the third term will give me a 6. K is equal to 2 times 4 is going to give me an 8 for this fourth term. And for this bonus one, for this fifth term, K is equal to 2 times 5, which is 10. And that's how we can define a rule of a sequence. You know the drill. We've got practice set and you have some additional problems. Do all of the practice set, do the assigned problems for the other set, and make sure you check your answers. Listen, I look forward to talking to you soon. Make sure you understand what you're doing. Ask me for help. Find me. Contact me some way so we can assist you if you need any help before our next meeting. Take care. Look forward to seeing you soon, sweetie. Bye-bye.